Okay, and it's live. Alright, so I'm going to be designing a power supply. So, hi, my name's Mike. I've done this kind of thing before, and I just want to go through all the different steps of getting something together. Probably be doing this for about a month or two or so until it gets done, just depending upon my schedule. Hopefully be able to do it around this time on Saturdays. So, first, the particular device that I'm going to be doing is going to be able to take a rather high voltage, high current input. So I went ahead and looked around and was able to get a good deal on a 48 volt, 600 watt power supply. So that's going to be everything to feed this thing. And then for output, I'm looking to try to do up to 20 volts at about 20 amps or so. And that way any losses I get in the system, I don't have to worry about it too much, because you will lose between changing different voltages and everything. It will be a programmable supply, so you'll be able to do a lot more than just one voltage out of it. And hopefully by the time I'm done with this, I'll be able to put together something so that even if people don't need to use as much voltage or anything else, it'll be a nice little template or something for people to be able to design their own things with. So, without further ado, the first part. So normally when you're doing something like that, you end up with a idea, something from a friend or whatnot is like, hey, let's do a thing. So I have a sketch that I put together of how I figure I'm going to go ahead and control this. So a lot of this I've done before in the past of what I might need and whatnot. And this is 90% of the only part of this that I've designed so far. Is I've picked out a couple of parts and figured out some of the math for setting the voltage. So you're going to go ahead and see everything that I'm going to have to do from scratch, from this sketch and a couple of formulas in Excel to an actual output device. So, excuse me. So, first thing, I have the sketch in front of me, so I don't need this anymore. And let me go ahead and make this large enough so that we can see chat if anybody shows up. There we go. Alright, so the first thing that we need to do is we need to do a block diagram of exactly what we're going to be doing in our schematic. So, a lot of times if you've worked with a CAD program before or done something like this, you just have your spreadsheet, or not your spreadsheet, sorry, your schematic, and you throw your parts on there, and they're just generally, you fit as much as you can on the page. You can zoom in and out, so you just keep filling more. I want to do something that's a little more structured and show you kind of some of the ways that I'm going to go ahead and do that. So the first thing is you always want to have, if you're going to be doing a more complicated device, more than just a few parts, you want to try to break it up into different sections. And the way that you're going to be able to do that is by having a block diagram of what you're going to be doing. If it ends up that your individual device or whatever that you're making ends up simple enough that it's only one or two sheets, you won't necessarily need a block diagram. If it gets much larger than that, what the block diagram's going to do is on each one of your sheets, as you put a piece together, you're going to be able to go back to the block diagram and say, hey, this is on this schematic page and this schematic page, and it's going to let you put together your table of contents a lot easier. So, and then this is just a simple matter of just drawing things. So we just go ahead and draw on the symbols layer, And first thing is going to be just a simple rectangle. And that's going to probably be our microcontroller. We're going to have another one. That's going to be our power supply in. So those two will be controlled together like this. That's going to start our power supply. By power supply, I mean that's actually going to be the input supply. We'll go ahead and put that there. Microcontroller. There we go. And we're just going to keep doing that with the different parts that I've got on here. So the micro is going to go out to USB again. There's our USB interface. Possibly, depending upon how things go, there might be a GPIB interface. Why GPIB? Well, there's a lot of good equipment out on YouTube, on eBay and stuff like that, old used equipment that you could use for like desktop multimeters and stuff like that, that'll have a higher resolution, they'll have a higher sampling rate and everything else. A lot of those don't have USB. They barely even have serial, but what they do have is what used to be called HPIB or GPIB. And we can control that equipment with this, possibly, if I can go ahead and get that sorted. So GPIB, and this is all rough, but this is just planning. So you want to get all this stuff down and get this planned out, because along the way, this will also be your reminders of, have I done this yet? Have I been able to figure this out yet? So some of the stuff I might not be able to figure out, hey, but this is going to help me succeed despite my failures. USB. There we go. So the other thing that we're going to need is that we are going to need a controller that actually changes our voltage into the output that we want. And that's actually going to be a very important part of this. So that's going to have to talk to the micro somehow. And this is going to be our, since we're going from a higher voltage to a lower voltage DC, this is going to be a buck controller. And why buck controller and not just buck chip? Well, with the kind of currents, I don't want them going through this. I want them going through nice, big, beefy MOSFETs. And I'll show you that a little bit later as I'm putting the stuff together. So what a buck controller does is it controls a couple of MOSFETs. I believe this one uses N-channel MOSFETs. And what it's going to do is it's going to basically pump them on and off. And then all the current is actually going to be absorbed by those. Big beefy parts connected directly to the ground plane on the board and everything. They're going to be able to handle something like 140 amps a piece or something like that. So they're going to be able to absorb all of this, and it's going to be a lot easier to control them. A small discrete component on the board that does all of that internally is going to be a lot more of a nightmare and more expensive to deal with. And the buck controller is going to be let us go ahead and play around with different MOSFETs to find some that'll actually fit our need. The microcontroller, whoop, that's not what I wanted, that one. So the microcontroller is also going to control a couple of other components. Which are going to be digital potentiometers. Or digipots. Why not? So what the digipots are going to do is on a lot of bench power supplies, you will have the knobs on the front, which are basically rheostats, which change a voltage divider that actually will change what the buck controller or buck converter will actually output. Or if you have a simpler thing, just a regulator. And what it does is that basically will feed a certain voltage back to a comparator inside the converter, or the controller, or the regulator, or whatever it is. And it will try to bring that voltage back to a stored set voltage that's in it. On this one, and I'll show you the data sheet, it wants a 1.25 volts. So the way we do that is we just set up a simple resistor ladder using digital potentiometers, and then this way we can use I squared C, or I think one of them's I squared C, the other one's SPI, and we can actually set the resistance and just give ourselves a nice little resistor ladder that we can change on the fly. Alright, so we've got one there, and we're going to need at least one more here. Now, of course, this is just going on rough. Clean it up later, but this gets us started. And we're going to go ahead and make a copy of you. You can use your own program if you're doing this. I don't care. I know this last week, Eagle pissed off a lot of people with their new pricing structure thing. I don't care. I've used this version of it for a little bit, and I've bought it, and it doesn't go away. So before this, I'd used other layout software for like 10 years, because you don't really need to change it that often unless you're heavily into, a lot of the other stuff. So who knows? Don't want to get into that. So I'm just using Eagle because it's what I have and what I'm familiar with. Let's go ahead and move that there. Alright, so, and I know that SPI, this is going to be an SPI interface, and I know that this one is I2C, because this one is going to be an I squared C interface. And I've already done some looking at these parts, because the actual buck controller that I'm going to use and the digipots are actually more important than the rest of the system combined, because getting that selectability, and with the kind of voltages that this power supply is going to be throwing around, I need to actually be very careful with those. So in addition to that, the buck controller is going to have a pair of MOSFETs that it's going to be driving. Alright. So high side MOSFET, low side MOSFET, this is our output, filtering, and then we've got current sense, From the current sense, this goes out to... This is going to go ahead and go out to device under test. So this is our voltage output. The current sense is also going to feed back into the buck controller, and that tells it if it's going to have too much current. And then what is going to happen is, off of the output from the current sense, is we are going to have... There we go. Is there's going to be the resistor ladder that goes between these two digipods. And that's going to feed back into the buck controller to set our voltage output. So that's basically the loop. Input supply is going to have to supply the high side FET. So basically what the operation is that we've got an input supply, 48 volts. That comes in here. We've got our output, which is going to be 2 to 20 volts. And it's only that because I haven't figured out how to get it reliably lower than that. But hey, I'll learn. I might be able to get that down to 0. Oh, excuse me for a second. Yeah, don't want to cough. I need an easier button to muting myself. Anyways. Alright, and that goes out to ground like that. So what's going to end up happening is the input supply is going to be feeding us juice. There we go. Easier to see. That juice is going to go down. The buck controller is going to turn on and off the high side supply, which is going to give us a nice, or ugly, it just depends on how much current's going through it, waveform. So the duty cycle is going to set how much actual voltage is going to come out of that. Then once the wave on the high side gets exactly where it needs to be, it shuts off the high side and then turns on the low side in order to ground it out. When you're dealing with large currents, you actually need to, instead of just turn it off, you also need to find something to block the spigot with. So that's how that happens. So that basically is going to pulse the 48 volts, and then those pulses are going to go through a series of either some capacitors that are going to be connected to ground, inductors, and some other devices to go ahead and actually clip and clap and get rid of a lot of the higher voltage noise. This buck controller, I think, is going to be around 150 to 200 kilohertz. So it's going to clean up that noise. So what eventually goes out is flat to within, a few tenths of a millivolt, or maybe millivolts, or maybe more than that. We don't know. We're going to get there. So that's basically how that's going to work. So now we've got a lot of different parts here that we can go ahead and actually start putting into this whole system. So the first one is I want to get the, let's go ahead and go with the micro for this. So I've got some stuff here that I've pulled out a couple of possible things to use. So the first one is I've got what's called the teensy. So somebody went ahead and said, hey, use this. I'm like, okay, because he's going to be working on the programming for me, and that's going to be great. So now I have this teensy board that I need to somehow connect to a circuit board. So how am I going to go ahead and do that? Well, I need to build a part in Eagle for this teensy. So we're going to go ahead and open library. And Eagle's got a bunch of different libraries. I know for a fact that they don't have one for a teensy. So let's go ahead and do it this way. Let's file, new, library. So we're going to do a new library, save as, and we're just going to call this one power supply stream. There, I'm not going to get it confused with anything else. Alright. And then everything that I'm building in that one will be available when this is done. So first part of it is we need to make a new device. So our new device is going to be, how is it spelled? T-E-E teensy 3.2. Okay, yes, we have our new device. First part is the schematic symbol, so teensy 3.2. So this teensy has a bunch of pins on it. So let me see, 0 through 12, ground, 13, 23. So if nothing else, that's what, 12, 24, 26, 27, 28, 29, 30, 31. And it looks like a few others, so let's go ahead and start with that. 31 pins. Pin. So teensy's laid out like that. We'll go ahead and lay it out like that. So ground is 0, so 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The reason why I'm doing it like that is so that it goes ahead and numbers them for me. Because that way I don't make as many mistakes. 13, 14, up to 23. Alright, and then the rest of them I can just do whatever I want. So A ground, V in, 0, ground, VBAT, 3.3, ground, program, A14 DAC. Alright, so we've got our pins. And let's go ahead and move them as a group. And let's make this actually look somewhat decent, because we're going to eventually have to read all this. Right. Come on. Go back to... Alright, and let's start renaming some stuff. GND. And this one is 0. 1, 2, and this is boring, but fine. there we go. And we now have a teensy, mostly for our schematic. So the next thing we're going to do is we're going to add a text field that is called greater than name. And then greater than ref. No, this one's different. Sorry, it's not ref. It is... Let's save this a second. Here, let me open another library real quick. I've lost my mind. Value. There we go. And that's it. That is the entire part. Well, for the schematic. Now the other part of this is that the teensy, I'm going to have to figure this out later, but I think it's 10th inch centers. So actually, let me just go ahead and find that out. So, so let's go ahead and see if we can't find a data sheet on this guy. Software development tools, breadboard usage is available with header pins. So if it uses header pins, that's 10th inch centers. Alright, easy enough. Hooray, simple. So the next thing we're going to do is we are going to build a package for it. 3.2. Yes, new package. Alright, so there's a real easy way to do this. Set your snap grid. Right now it's 0.05. That means every 2 squares on the grid is 1/10 of an inch. So we're going to go ahead and put down some pads. These are through hole. And we're going to, right now, go ahead and set them to circular. Good enough. So we need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Why not? Let's just go all the way around. So that's 1, 2, 3, 4. 1, 2, 3, 4, 5. And then back the other way. Alright, and that should let us put the teensy directly on the board. Kind of. So we want to do something a little more than that. We want to make sure that this, on the place layer, dimension, origin, names, seal that. So we're going to make sure we're on the dimension layer. We're going to make a nice looking little outline that says where our teensy is going to be going. Then on the placement layer, the teensy has this USB right here. So what we want to make sure is when we're actually doing our placement, we're going to put this out here. And that's going to give us a little bit of an orientation on where that's going to go. If we've got tall components hanging off of that, we're not going to be able to plug in the USB, and that's not going to be that useful. So we want to go ahead and make sure that that's on there. Again, enter text. So we're going to need name. Let's put it on the right layer. And that's actually really important that you make sure to put this kind of stuff on the right layer when you're putting it down. Because if the name doesn't go in the names layer, then when you actually are having to hide layers or when you produce your Gerbers, some of your silkscreen names aren't going to be there. And if your silkscreen doesn't make it onto the board, you don't know what's what. Obviously on a teensy, you're going to be able to figure out what part it is because there's not going to be another part that looks exactly like that. Other parts, that's going to be a big problem. If you've got 1,000 capacitors on your board or something like that, and you don't put any of the reference designators or anything on that, you're either going to be lost or you're Apple. Subtle dig. Because they don't label a damn thing on those motherboards. Makes them fun to repair. Alright. And we're also going to put value. And we can always go ahead and move that around. So what ends up happening is when we actually move this into the schematic, or we put it into our board or anything else, the reason for those the caret at the front there is what the eagle's going to do automatically is it's going to replace that with whatever the device ends up actually being. So that's a field that it's going to be filling in later. And when I show you how to basically set up the schematic sheets with a header, you're going to be able to see that is that you can go ahead and set values for various different things like who drew it, what the date is, and that kind of stuff automatically, and then Eagle will actually fill that in as you go. So, for now, we're just building a part. Alright, let's go ahead and save that. Are these going to be the right size right now? Probably not. I'm just doing this as a demonstration. We can always edit this later. So now we've got this down, and that's going to give us a place to put our teensy. And you can see how everything's probably not the right size, but who cares? There, that looks smaller. Good enough. So now we go ahead and open our device, and everything's empty. So here comes the fun part. So first what we're going to do is we're going to add the actual captured schematic representation for this. And that's going to have all of our various different names and whatnot on it. Now we add a package by hitting New, and we add that package we just made. And I've miscounted. The package doesn't have enough pads. So yes, I miscounted. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Alright, so we go back, and like I said, we can always fix it later. So, ground 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There we go. Yay, easily fixed. Alright, let's go back to U, New. And now we're going to add it, and it's going to have enough. And it says, hey, we need to now connect all the pins. So the pin on this side, it says gate 01.0. These are the actual names that I put on here. On this, remember as we counted around the chip, they're all going to be in order. So the first one is we have ground. So ground is pin 1. Connect. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. VBAT 3.3. Ground 1. Program DAC. And then around the next way, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 3.3 out, A ground, and V in. And then we will go ahead and double check that later. Okay, and now we have a check mark, which means that every single net is actually connected to a pad on the unit. Value can be on or off. That just gives the name of the part. So we'll just say on, and it'll name it for us in the schematic. If we say off, it actually is not going to tell us what the name of it is. And you'll notice that this says G $1 and then caret value. So if we set prefix to U for microprocessor, a lot of times this stuff will be U. It could be a connector. If this is connected with a jumper, it'll be J, whatever. So we'll go ahead and just set that as U. And we'll set the value on. And we'll save this. So now, if we go to our schematic and we open up a second page, new, description, microcontroller, And remember what I said about labeling these as we go. So now this is sheet 2. There we go. So we go to sheet 2 and then we add the part that we just created that we'll probably have to fix later, but it's fine. And we called this, what did we call that? Power supply stream. So it might not see it. Nope, it doesn't see it right now. So what we might have to do is go here, libraries, custom device, power supply stream, and see this little green dot here? We just have to tell it, yes, we're using that library, and then it adds it up there. There we go. Alright, let's try that again. And now power supply, teensy. And now we have our teensy in, and we can go ahead and connect what we need to connect. And you'll see that this says like P1, 2, 3, 4. We can go ahead and fix that later. This is just a matter of going ahead and getting this guy in. Alright, so that was the first part. Let's go ahead and end this on this, and I will go ahead and try this again a little more. So let me go ahead and make sure all this worked, and then I will start this back up. But this will get archived. Yay! Little chunks. Thank you for watching this. Obviously not live, but hey.